Hello and welcome to another video on the Oscillators app. I've added some functionality that I'd like to demonstrate in this video, and I've also updated the GitHub repo with some instructions on how to get the project up running on your own machine. And also for the perspective, I've added some information on what this is sort of about and why it's kind of useful to even have oscillators. And some of the examples that I came up with here are, for example, controlling really fast motors used in, for example, selective laser sintering SLS, or another example that I like is the electric candles one. If you think that you're out for a candlelight dinner and that candle might be powered by a microcontroller, which is sort of playing a pre-recorded pattern for the way that it flickers and not really true randomness. And generally, a microcontroller is obviously a pretty complex machine, right? It's a full computer technically. And well, with a few oscillators, you could achieve such a pattern with much less resources technically on a circuit level. Okay, so let's look a little bit into how far the app is, how far it's come. What I've demonstrated in the last video was that you can choose different target functions, which is here in the top left corner. So for example, now we have a sine. I've selected a triangle now, and you can change its parameters. For example, we can increase the frequency slightly, and we'll see in a second that it updates. And well, this is just cut off because we have a fixed 1 second window here. This is new, and that's also new. For concept, this is our pool of oscillators, what I like to call the ensemble. And this is the sum of the oscillator signals across across the y-axis. Well, along the x-axis, but we sum each y. So for example, if we look at this point, we have 1, 1, 1, and we see indeed here we have 3. And now the goal is, how can we use fixed frequency sine oscillators, which are of course quite smooth, to approximate a jagged triangle function. And this menu is new compared to the last video, where we can select the wave type. I have sine selected. This doesn't work yet, but we'll come to that later. Let's talk about the algorithm that we can choose. So we have linear regression. I have implemented a few other algorithms, and since linear regression is a classic algorithm, I'll just stick to that for now. And we can click optimize, and it already reports that optimization is finished. And we'll see an updated approximate function to our target function. And yeah, it's not a perfect triangle, but it is, I suppose, more triangly than it was before. And we can see here that we have a quite fast oscillator at the top, a medium speed one in the middle, and a quite slow one at the bottom. This is where the frequency range comes into play. So what this frequency range says is that we are now sampling sinusoidal oscillators with a frequency range from 0 to 10 on a uniform distribution. So min is 0, max is 10, and we can, in theory, well, I've limited in the GUI to 0 to 10, but we can, of course, in theory, make this 1,000 and thus increase the search space. The perturbations is a reflection of how much time or resources or energy we are willing to spend. Let's just say resources in this case, but perturbations really is individual changes to an oscillator with our optimization algorithm. Actually, the linear regression algorithm doesn't use the perturbation parameter, so this is a bit yeah, not ideal at the moment, because I'm just using sklearn, and that didn't really have a way for me to limit the resources or optimization steps. So a manual implementation could make use of the perturbations, but the other algorithms that I've implemented myself do make use of the perturbation parameter. Okay, so we see that we have 3 oscillators, and as we might expect, increasing the number of oscillators will allow us to more finely approximate our target function. Okay, now that we're at 6 oscillators, let's use linear regression to optimize again. And we see here now the sum is 6, that all checks out. And our target function is unchanged. Optimization is completed, it's just rendering the GIF. Okay, well, that looks worse actually, in my opinion. This is interesting. But, well, yeah, I don't really have an explanation for why that would have happened. Let's see what happens if we change it up to 12. We run the optimization again. This peak kind of looks good. That peak is too large. I mean, it is roughly the thing. I'm not too unsatisfied. Also, the amplitude matches quite well, 0.6, 0.8. So it's not fully there yet, but with the number of oscillators that we have, yeah, not too shabby. And again, these are the individual oscillators. It's getting a bit complex to oversee, and what is also maybe somewhat unideal is that we have this cutoff thing, which is due to the 1 second cutoff, like the edge there. But yeah, let's see if we can do the reverse thing, approximating a sine function of, well, somewhat increased frequency, but now with a set of triangles. Okay, we click optimize. Our result shows it's also not super perfect, but we have, well, no, it's actually pretty horrible. I won't try to sweet talk it. Okay, I found one where I think it's a not too bad of an example. It's the relatively fast, I would say, probably 6 Hertz sine function as a target, and a range of 0 to 10 frequency inverse sawtooths, 12 of them in an ensemble. And the sum, it's not really the exact smoothness of the sine, but at least it matches the general speed of it. I think I'll have to increase the number of oscillators in order to improve performance. Okay, before I finish, I want to show some of the other optimization algorithms. 2 in particular. Let's select the triangle function here and stick to 3 oscillators so everything renders a little bit faster. Then we've already tried linear regression, which should find the optimal or an optimal solution to the approximation. But now for neuromorphic computing, what's more interesting, because it doesn't use gradient information opposed to linear regression, is the simple random walk algorithm. So what this algorithm does, it perturbs one of these oscillators randomly, like it just draws from a random distribution, reinitializes it, and then does a comparison whether this ensemble sum is better than has a lower root mean square error or whatever loss function you might want to use here compared to the original oscillator that we had beforehand before the perturbation. So let's try this one. And here we have little TQDM weighting bar, and this is our result after 100 perturbations. But of course we can also increase our perturbations, in essence our resources, and let's see if we get a better result here. took a little bit longer. We have to wait for the UI to update. Okay, interesting. Let's see what happens with 10,000. Now, the idea is also that while this is pretty slow on my digital computer, that on a circuit, an optimized circuit, this might be much faster than what's happening on my digital computer. And this is quite a bit better, I think. Let's see if we can push this to, say, 50,000. And get an even better result. What I also love about this is that it shows how powerful random search is. Well, let's go back to linear regression and see sort of what our optimal result was. Okay, well, probably doesn't get much better than this. We also have this Las Vegas algorithm, which starts out with just, well, that's definitely freezing the UI. Okay, that shouldn't happen. There's some threading problems going on that I need to sort out. So it starts out with just one oscillator in the ensemble, and then keeps adding oscillators only if they ever reduce the root mean square error. Compared to the previous ensemble. Okay, well, it's not working super well yet. I hope that I can show it working better in the future. Ultimately, it is not just part of working as in like the app or program works as intended, but of course it's also a matter of optimizing parameters. So an optimal parameter identification algorithm, aka hyperparameter search, could also be part of this. And yeah, I find this quite fun, and ultimately what I'd like to do is to build some of this circuitry IRL physically, but having this as a suit to explore what parameters and, for example, wave types are good is really interesting. I have, of course, already done some more extensive research on this, but without a GUI, and just playing with a GUI I think is really nice to show other people what's going on, and it makes it a lot more fun than just looking at the plots that come out of some search. Okay, thank you for watching and have a good day.